In the previous modules, we had been looking at the single equation estimation methods for simultaneous equation models. We had been looking at the indirect least square method and the two-stage least square method. In today's lecture, we will be looking at two other different methods. One of them is the limited information maximum likelihood method. Being a maximum likelihood method, it has very nice properties, but generally this is very difficult to solve, as we will see. An alternative method is the least variance ratio method. Now, the least variance ratio method is intuitively very simple, and what happens is that the limited information maximum likelihood and the least variance ratio methods lead to the same estimates. We will also see where they actually coincide. The limited information maximum likelihood method of estimating the parameters of a single equation of a system of simultaneous equations. In this case, as before, we are interested in estimating the parameters of the jth equation with yj as the response variable, this is small y, and capital Yj as the other endogenous variables which are included in the model. Xj's are the exogenous variables which are included in the model. So, there are Gj endogenous variables including the small y and Kj exogenous variables in the model. The parameters are beta j star for the endogenous variables and the gamma j stars for the exogenous variable, and we have the error as Uj. So, this is the jth equation as we had been previously looking at. And our aim in this case is to estimate the parameters beta j star and gamma j star. Now, what is the LIML method? The limited information maximum likelihood is an alternative to the ILS and the 2SLS method. Remember, both ILS and 2SLS methods are also single equation estimation methods. So, this is a third alternative of a single equation estimation method. However, owing to computational complexity, the 2SLS is very often preferred. Of course, the ILS is simpler, but remember that the ILS cannot be used unless you have exactly identified equations. So, if you have over identified equations, then the indirect least squares does not work, and the 2SLS or the LIML also works, but 2SLS definitely is computationally simpler and hence preferred. Also, the derivation of the LIML is rigorous and often difficult. Of course, that can be done, but it requires a lot of mathematics, and hence recourse is often taken to the least variance ratio method. This is a fourth alternative, and fortunately for us, the mathematics is simple and it also reduces to the same estimator as the LIML. So, at some point which we will discuss, the two methods converge. So, if you look at the least variance ratio estimator, which is computationally simpler, intuitively simpler, it actually gives you the same as the LIML estimator. We will just give you an idea of what the LIML estimator is, but we will not go into great details of estimating through the LIML method. Now, what is the LIML method? To look at that, let us go back and look at the structural model. So, the structural model for the whole system is By plus gamma x is equal to U. That is for the G endogenous and the K exogenous variables. Without loss of generality, let us assume that the jth row of A is the whole parameter set, that is, it consists of B and gamma, and the jth row of A is 1 minus beta j star prime 0 prime minus gamma j star prime and 0 prime. Remember, beta j star and gamma j star are the parameters for the jth equation, and we have zeros because some of the endogenous variables, which is capital G minus small g j, and some of the exogenous variables, which is capital K minus small k j, are missing. So, their coefficients are 0. Why did we write this as without loss of generality? Because we are assuming that the variables which are present comes in first and the variables which are absent comes in later. So, we are just reorienting the variables and we write the vector as 1 minus beta j, 0 minus gamma j and 0. The reduced form is as before, y is equal to pi x plus b, which we obtain from the structural model by taking the inverse of b, and we have the relation that b pi is equal to minus gamma. This we have seen before as well. So, we have the structural model, we have the reduced form model, and we have the jth equation parameters in terms of the structural model. Now, for the jth equation parameters, if we use the relationship between the reduced form and the structural form, we get, after some simplification, 1 minus beta j star prime 0 prime into pi is equal to gamma j star into 0 prime. So, we can write the jth equation parameters in terms of the relationship between the structural and reduced form parameters. Now, if we partition pi as pi 1 1, which is of order g j by k j, pi 1 2, which is of order g j by k minus k j, and similarly pi 2 1 and pi 2 2, what we can do is that we have, substituting this in the previous equation for the jth equation, we have 1 minus beta j star prime is pi 1 1 into gamma j star prime, and 1 minus beta j star prime into pi 1 2 is equal to 0 prime. So, the first is a set of k j equations and the second is a set of k minus k j equations. Look at the orders of pi. Pi 1 1 is g j by k j, and similarly 1 minus beta j star has g j elements, and pi 1 2 is again g j by k minus k j, again the multiplication goes through. So, we have two sets of equations if we use this, we use the partition of pi. And if you look at the first estimate, we first estimate pi from the reduced form. So, you put the estimates of pi in these two sets of equations. So, the two sets of equations now only has beta j and gamma j as the unknowns. And what we can do is that we can first look at the second set of equations. Notice that the second set of equations, the k minus k j equations, do not involve gamma j star. It only has beta j star and the estimated pi 1 2 hat. So, if we can solve beta j star from this, we get an initial estimate for beta j star from here. And then using this beta j star in the first equation, now we have the estimate of beta j star, we have pi 1 1 hat also. So, the only unknown in the first equation becomes your gamma j star. So, if you use this beta j star in the first equation, we can solve for the gamma j star from the first equation itself. So, this is what the LIML does, but there are certain constraints to this. Let us look at these constraints. So, what is the condition under which 2 can be solved? That is the second equation. It looks like a homogeneous equation, but it actually is not. Let us see what it is like. Now, if I write pi 1 2, which is of order, mind you, g j by k minus k j, if I write this, break this up, we can write this in a more compact form, this second equation. But before that, let us look at the condition that we have. We have the jth equation, if it is identified, which it has to be because we are estimating its parameters, then k minus k j must exceed g j minus 1 or must be equal to it. Okay. So, what we can say is that rank of pi 1 2 can only be either g j or g j minus 1. Why do you say that? Because k minus k j, if it is equal to g j minus 1, then obviously the rank condition also says that the number of parameters to be estimated in this case, it says that if you have exactly identified equation, then you need to have g j minus 1 rank. So, the rank of this must either be g j or g j minus 1, it cannot exceed g j, it is the order, and k minus k j being always greater than this, that does not create any problem. The number of columns does not generally create any problem. So, we have a rank condition. Now, let us look at this condition on the rank. Let us write pi 1 2 as pi 1 2 hat is pi hat, which is a vector, a k minus k j dimensional vector, which is basically the first row of pi 1 2 hat, and the remaining rows of, that is g j minus 1 rows of pi 1 2 hat, we will now call pi 1 2 hat star. So, if we break up pi 1 2 hat this way, then we will end up with 2 as pi 1 2 hat star prime beta j star is equal to pi hat. Mind you, we had 1 minus beta j star into pi 1 2 equal to 0. So, the 1 goes with the pi small pi and beta j goes with the pi 1 2 hat star, and we have a set of non-homogeneous equation in this case. We will call this 3. Now, this non-homogeneous system of equations in 3 can be uniquely solved if the rank of pi 1 2 hat star is equal to g j minus 1. So, we need to restrict the rank to g j minus 1, it cannot be g j as such. So, we had a choice, it could have been g j minus 1 or g j, but for the homogeneous system to be solved, we need that rank of pi 1 2 hat is g j minus 1. But unfortunately, as you know, when you are dealing with data, it is always from the sample observation, you always get the rank of pi 1 2 hat as g j, you get it as full rank. So, in this case what happens is that the rank exceeds. So, what you need to do is to use the restriction that rank of pi 1 2 hat must be equal to g j minus 1 and then solve the maximum likelihood. So, in this case we have the LIML method maximizes the likelihood function based on the g j endogenous variables subject to the restriction 4, which is subject to the restriction that rank of pi 1 2 hat is equal to g j minus 1. This is difficult, but not impossible. It can be mathematically shown, but the mathematical is rather cumbrous and tedious. So, we will omit the mathematics here, and instead what we will do is we will look at the least variance ratio method, and we will see its relation with the LIML method. Now, if you look at the least variance method, we go back to the single equation that we are looking at, the jth equation, which is y j is equal to capital Yj beta j star xj gamma j star plus uj. And now bring all the endogenous variables to the left hand side. So, we write Yj minus capital Yj prime beta j star is equal to xj prime gamma j star plus uj. Now, if you write this left hand side as Yj star eta j, where Yj star is equal to small yj and yj prime, and eta j as 1 minus beta j star, then let us assume in 1 is this equation that we have got now, we assume that eta j is known. So, if eta j is known, the left hand side is known. So, it can act as a response. So, yj star prime eta j acts as the response, and we want to estimate gamma j star from here. So, we are regressing yj star eta j on xj. So, applying the least squares to 1, what we get is the least square estimators, and from that we can calculate the residual sum of squares. The RSS now comes out in terms of the eta j's, mind you, we are assuming the eta j is known for the time being, and the RSS comes out as before, which is the usually the response y prime y minus y prime x prime x inverse x prime beta, which in our terms would come out to be this. And what we have is that if you simplify this, take the eta j's on either side, we have eta j prime wj eta j. Now, wj is basically from the data, and eta j's are the unknowns, okay, which we have assumed till now to be known. This is the first RSS that we get. Alternatively, if we regress yj star eta j on the whole set of exogenous variables, not only on the given set xj, then we can again recalculate the OLS and hence the RSS, and we get eta j prime w eta j as our RSS now. So, the difference between the two RSS is only in the w. One is wj, which is based on the xj's, and the other is w, which is based on the x's, all the x's. Now, what would you expect? You would expect that the RSS would be smaller than RSS star, because the more variables you have, the better would be the estimator. X has more variables, xj is just a subset of it. So, you would be expecting this. But since we have built the model on the basis of xj, we have reasons to believe that xj is good enough. So, we would expect that RSS and RSS star would be almost equal. So, if that is so, what the LVR method does is that it tries to minimize the ratio between the two RSS. So, you see the numerator is the RSS star and the denominator is the RSS. So, obviously, this is going to be greater than 1 because RSS star is larger, and we want to make it as close to 1 as possible. So, we try to minimize this ratio. That is what the LVR actually does. And at this stage, I will tell you that the LIML also reduces to the same condition, that you minimize this ratio L eta j prime wj eta j by eta j prime w eta j. So, the LIML and the LVR becomes identical from this stage onwards. So, both minimizes the ratio L, and this should be with respect to the parameter eta j, which we had been assuming known, but which are actually unknown. So, what are the conditions for this? So, delta L delta eta j equal to 0, and this leads us to a very simple condition of wj minus Lw eta j is equal to 0. This, after a little simplification, this is what we get. And if you want to solve this equation 2, then what we have to have is, it will have a non-trivial solution if only we have the condition that the determinant of wj minus Lw is equal to 0. Now, if you look at this condition 3 is a polynomial in L. So, we can solve this polynomial, and this will give us the respective roots. Since we are trying to minimize L, we will look at the smallest root lambda minimum, and lambda minimum would give us the L value which would actually minimize the ratio. So, what is the LVRS ratio? So, if you substitute lambda min in 2, we now have Wj minus lambda min W eta j equal to 0. So, lambda min now stands in place of L, it gives you the minimum of L, and we can solve eta j from this. This is a set of homogeneous equations and you can solve eta j from this. Now, any multiple solution of eta j will also be a solution. So, you get a eta j and if you multiply it by C, it also becomes a solution. But remember what eta j is, it was 1 and minus beta j star. So, it is uniquely defined for you just take the solution which has the first element equal to unity. The rest of the elements would give you your beta j star with the negative sign. Once you have got the beta j star, now you can construct y j star eta j hat and then regress this on x j, and we can now estimate the gamma j star directly. So, now you can go back, before we had assumed eta j known, now you have estimated eta j, go back to the same set of equations with eta j known now, and if you regress now, the OLS would lead you to gamma j star. You can use the OLS because we have the x j's only on the right hand side. So, there is no correlation. So, this is the LVR estimator, and as we said that the LIML also reduces to minimization of L, and hence the LIML and the LVR ratio ultimately leads to the same estimator. In today's lecture, we looked at the limited information maximum likelihood method and saw the difficulties in actually deriving the estimates for it. However, we saw that the least variance ratio method, which is much simpler to understand as well as to derive, leads to the same estimator as the LIML does. So, in fact, these two methods can be almost taken to be similar. So, what we have done till now is that we have looked at the indirect least squares, the two stage least squares, the LIML and the LVR methods. Of course, given its simplicity, the two stage least square is probably the most popular among these estimators.